So in chapter 28, we talk about the interaction between the magnetic field and the charged particle, or more precisely, the moving charged particle. If a charged particle is moving in the magnetic field, then there will be a force acting on the charged particle, which is called the Lorentz Force. We'll use FB equals Q V cross B, or FB equals I L cross B to determine the Lorentz force. So now in chapter 29, we will see how we can generate the magnetic field, or how we can evaluate the magnitude or direction of the magnetic field. Actually, in this chapter, we'll learn the Ampere's law. So in chapter 23, we already learned Gauss' law, and in this chapter, we'll learn Ampere's law, which is more related to the magnetic field. And in the next chapter, we'll learn the Faraday's law. Actually, for chapter 32, we will also see the other version of the Gauss law for the magnetic field. But you can see, for the Gauss law, on the right hand side we have the Q enclosed, or this integration. But for the magnetic field, we don't. We only have 0 on the right side, because we don't have magnetic monopole, as I mentioned in the previous chapter. So now let's consider how to determine the magnetic field. So here we have a wire on this figure. You can see a wire and then a current going from roughly bottom to top. And we don't really assume the current, the wire is straight. It could be curvy. So we need to separate into many small segments, ds, and then of course, like similar to before, it would be a vector. ds is a vector, and the direction of the vector is the tangent direction to the wire at that point. And there may be 2 directions, but the direction will follow the current direction. So as long as the current is going from bottom to top, so for the ds at this point to the top left direction. So as long as we have a curvy wire with current, then it will generate magnetic field in the whole space. So the magnitude of the field, dB, dB is the B field generated at the point P by this small segment. And if you would like to determine the overall B field generated by this wire, then you need to integrate ds over the whole wire. But at least we first need to know how large dB is, referring to this small segment ds. So it is expressed like this. On the left side we have dB, and then on the right side we have mu0 over 4 pi. So in chapter 21 we know that epsilon naught is a constant called a permittivity constant, which is generally used for the electrostatics. Now we have another constant called the permeability constant, mu0. So the value is 4 pi times 10 to minus 7, 4 pi times 10 to minus 7 Tesla meter per ampere. Okay, so we have a mu naught over 4 pi. So we also have 4 pi here. So this term is simply 10 to minus 7 power. 10 to minus 7 power. So this is a constant term. This is a constant term. And here we have I ds sine theta. I ds sine theta over r square. Over r square. It is somehow like the Lorentz force. Like the Coulomb force, somehow like the Coulomb force, but actually not the same. Actually, when you see the Coulomb force, you have Coulomb force. You have F equals 1 over 4 pi epsilon naught Q1 Q2 over r squared. So here you also see r squared here, and then here for the Lorentz for the Coulomb force you have 4 pi over epsilon naught. Here for mu naught go to the top rather than stay at the bottom. And yeah, so we still have this part. And then as you can see here, we have sine theta, so you can simply imagine it would be related to a cross product. So if we write it in a vector form, so we will have dB vector on the left hand side, and then on the right hand side we have I times ds cross the r hat, the unit vector in r direction, and over r squared. So the r hat is determined by this. You can see in this graph. So we have ds here and then point P, so that the r axis is this way, and then r hat is the direction pointing to this point P, and then the length of this vector is 1. So this is r hat. And actually this is called the law of Bo Sapphire. Bo Sapphire. Or sometimes we will call it Bo Sapphire Law. But yeah, actually the same. So any questions? Okay. So yeah, so here for a long straight wire carrying current I. So this is the wire. You can see at this point. This is actually a wire, but going into the page. So with a cross here. So in this case, for long straight wire, long means infinitely long. Infinitely long, going from in negative infinity to infinity, which means long. So for a long straight wire carrying a current I, the Bo Sapphire law gives for the magnitude of the magnetic field at a perpendicular distance out from the wire. So it will be somehow like this: mu 0 I 2 pi r. So it will appear in this true chapter for many times. So this is really important for this one. So it means that if we have a wire going in, for example here into the page, then the B field will look like this. So the magnetic field line are concentric circle, and as you can see, for the inner part it is more dense, then which means that the magnetic field with a smaller R will be stronger. So the magnetic field at the outer part will be weaker. So we have a mu 0 is a constant, of course, 4 pi times 10 to the minus 7, and I is the current of the wire, and then 2 pi is of course constant. So mainly related to the R. If we fix the I, then if R is larger, then B will be smaller. Okay. So likewise for semi-infinite straight wire, the magnitude of the magnetic field at a perpendicular distance R from the wire will be like this. Semi-infinite means from 0 to positive infinity. Then it is called semi-infinite. So actually this one is half of the top one. It's half of the top one, because for long straight wire means from minus infinity to positive infinity, and if now it is only 0 to infinity, so it is only half of it. So this is how we could derive this very important expression. Okay, so here, of course, we will use the Bo Sapphire Law. Here we have this expression, and for this figure, we assume we have a straight wire, long straight wire. So this wire is from negative infinity to positive infinity. For this, maybe we can call it S-axis. S-axis. So suppose we have a small segment here, which is ds. So this small segment is ds, and then what we concern is the magnetic field at this point P. So of course R is in this direction. From ds to point P, and then R hat is with a length 1. So R hat is defined like this. Okay, so ds is going from bottom to top, because the current, we assume the current is going from negative infinity to positive infinity. So ds pointing upward, and then R hat point to that side. So actually the direction of B field is dB is proportional to ds cross R. You can see here. Mu 0 is positive, I is positive, R squared is positive, 4 pi is positive. So all these constant, or maybe all these variables are positive. So the direction of dB should be the same as ds cross R hat. So it's ds cross R hat. So actually, you can use your right hand. You can use right hand rule to determine that dB should be going into the page. Because it is like ds cross R, so going into the page. So you can apply the right hand rule like this, ds cross R, and then you can see the dB going into the page. Or the other way is if we have a wire going this way, so the B field should be going if the current going upward, then also you can use right hand rule in the other way. You can use your forefinger, follow the direction of the B field, and then your finger of your thumb, your direction of your thumb will have the same direction as the current. So this is the other way to apply the right hand rule. So going back to here, so we know that a dB going into the page. So now we can just ignore the direction at this moment, and then we only consider the scalar form of the Bo Sapphire law. So B will be 2 times 0 to infinity dB, or actually it equals to minus infinity to infinity dB. So it go back to here. So it will be 2 times this integration from 0 to infinity. So now we can substitute this term into here. So 2 and 4 can be cancelled. So we have 2 pi mu 0 I. Mu 0 I is independent of a ds. So this term can be factored out. So we have sine theta here. Actually, sine theta is related to s. Sine theta is related to s because we assume 0 is here. So the length here is s, and then this is r. This is r. So r square theta and s are all related to each other. So using the Pythagorean theorem, so we know that small r is s squared plus capital R squared, and then quantity take the square root, and then sine theta, we know that sine theta is sine pi minus theta, pi minus theta. So this is theta, the angle between ds and r. So actually this is pi minus theta. But actually for sine, these two angles should be the same. So sine theta is like capital R over small s. Small r. This one. Yeah, capital R over small r. So we need to express it in s because we have ds here rather than dr. So we need to change r in terms of s. So we have s squared plus capital R squared. Capital R is a constant, so it would be fine to keep capital R. But we couldn't keep r because r would be a variable. Because as long as you have ds here, then r will change. Small r will change. Capital R won't change. S and small r are changing together. So we can keep capital R, but not small r. So for sine theta, we substitute by this term. So we will have, and also small r we will exchange by this square root of s squared plus capital R squared. So we have b equals to this one, and then we need to integrate it. It will be like this, Yeah. So this is the antiderivative of this function, and then we substitute s equals to infinity and s equal to 0, and then we subtract these two results. So it turns out to be mu 0 I over 2 pi r. Because as long as you have this term, you have a limit s tends to infinity s squared plus r squared, take the square root. This limit will be 1. And for limit s tends to 0, s over s squared plus s squared plus r squared. This one will be simply 0. So this one is 1. So b is mu 0 I over 2 pi r. Of course, if you need to get this integration, you need to make some u substitution, like you need to define s equals r tangent theta, something. You need to do this kind of substitution, then finally you can come up with this antiderivative. So finally we come up with this expression for a long straight wire, and here it also implies that if it is a semi straight wire, then it is only half of this value. So we have a 29.4 and 29.7 for long straight wire and semi-infinite straight wire. Any questions? So let's have a 10 minutes break.